Welcome, welcome, welcome. For those who are joining in Zoom, please feel free to introduce yourselves and where you're from in the chat. You can do that on YouTube too. We will be monitoring both chats as always, if you care, if you'd like to on YouTube. It's tradition in the chat here on Zoom. One last note as well for those who are joining on Zoom, if you want to talk to everybody and not just Chris and I, make sure that you change the little thing that says to from saying hosts and panelists to everyone to talk to everyone in the chat. Great to see you all joining from all across so far the continent. If anyone's international, let us know, and we'd love to hear where you're from. Lucky
hell, it's just down the road from me.
And lucky Jamie is in California, where it is sunny and beautiful. Always nice. It's actually quite sunny. It's really nice here too today. I don't know about where you are, Chris, but it's like bright blue skies.
Yeah, it's pretty nice. Yeah, saw some blue sky earlier. I debated checking out the sun to see what it's up to, but I didn't have. I was still prepping for this. I was still wearing the helmet that Spock wore in the original Star Treks, where they were teaching him stuff. That's what I was doing. is learned
all real quick.
Learning about stellar evolution. That's what I've been doing. So
I'm glad you have, because I know absolutely nothing about stellar evolution.
Yeah. So part of my challenge today is to see how well I can regurgitate and explain things.
Sounds good. Thank you for doing all the prep for this one. Really appreciate it.
Now, the folks at home don't see the pages of notes that I send you at the last moment.
It's very helpful, and Chris is an amazing volunteer who does a ton for us. So big thank you, and big thank you to all of our volunteers as well. Today we are talking about the life cycle of stars. And this is, as I've mentioned, a topic that I don't know much about. So Chris is going to do the majority of talking on this one. And I'm going to sit here and ask all of the questions that you're all too shy to ask.
Yeah, it's so my idea behind doing this topic today was that at this time of the year, I mean, most times of the year you can do this, but at this time of the year, you can go outside on a clear night and you can see examples of pretty much the gamut of stellar evolution from, depending on how late you want to stay up, from protostar all the way up to the main sequence, various classes of main sequence stars, all the way to supernova remnants and even a black hole companion. So knowing those are up in the sky, I thought, well, I'll run through a little bit about how that all works. I'll do my best to explain the physics behind it, the astrophysics behind it. But then mainly I want to share with you the targets so that people can make notes and say, oh, well, I can go here, I can look there, and I can see all these different examples. So it kind of really cool, in a way, cool way brings it all home. So let's see. And as I said, I've been spongifying the information. I did prepare a talk on this, on the life cycle of the sun some time ago, which touched on what the sun did, but then what the sun didn't do because it wasn't big enough. And so we're going to get into the more fun, exotic things that the bigger stars do as we go here. So basically, yeah, I want to start out. I'm just going to be looking at my notes the whole way through here. So what we're going to do is, let's see if I had this, I'll bring up this PowerPoint that I have. I'm going to dip into this PowerPoint from time to time. And let me share my slides so everybody can see it. Where is my, here we go. Share my screen. Go. Here we go. So yeah, I'm going to just sort of dip into this PowerPoint as we go here. So essentially, though, the way things work is that in the beginning, the sun, our solar system started out inside something like this, which is the Orion Nebula, and there's Orion's belt. See here, and just to zoom in on that a little bit, you can see the gas beautifully portrayed by a Hubble Space Telescope picture. And then if you zoom in on some of the little details in this, you can see little baby solar systems in these photographs that we can actually see the protostars and the protostellar disks around them, which will, one day turn into a proper star and a proper solar system. So here's kind of an artist's conception of what that might look like after about 100,000 years of that collapse. So basically you start out with this cold, very cold cloud of molecular hydrogen gas in one of the arms of the galaxy. And at some point, some random fluctuation will cause a little bit of maybe a pressure wave or something go through it, and it'll cause some of the gas to kind of bunch up. And as soon as it bunches up, then you start getting increased gravity, and that sort of then snowballs as more and more gas gets attracted into these clumps. And depending on the structure of the cloud, you can get multiple clumps happening at the same time. And eventually the end process of that will be a number of those little solar systems and basically an open star cluster. So when we see an open star cluster in the sky, like the Pleiades or the Hyades, which is the face of Taurus, and all the other really cool smaller ones that are out there, those are stars that have been formed out of a big molecular hydrogen cloud that have not yet dispersed in any significant way. So they're still in the nest with the rest of their siblings and not so much as individuals. And so this is the sort of time sequence we get. After about 3 million years, we have these protoplanetary disks. And once the star in the middle of this clump is gathering mass and accumulating mass. And as that does so, the gravity, the self-gravity increases to the point where the center of that spherical mass of gas is increasing in pressure, increasing in temperature. And at some point, you reach a threshold where you can hit ignition and start fusing the hydrogen atoms in the core of the star. And the result of that fusion process is the helium atom and energy. And so then the star begins to shine.
Hey, Chris.
Yeah, go ahead.
Real quick technical question right off the bat. What's the difference between molecular hydrogen and just hydrogen?
So it's non-ionized. So it's all tame, basically, if you want to think of it that way.
It's all what, sorry?
Kind of tame, not ionized, just sitting there hanging out.
Oh, so molecular hydrogen is like the two bits of hydrogen that have bonded together and are not actively live around and trying to interact with stuff.
Yeah, it could be an H2, a stable H2, that kind of thing.
I see. Okay. Thank you.
Without any particular energy source to ignite them or energize them or cause them to glow, because there's no, in the beginning, there's no star to do that. Once the stars start shining in that cloud, then we get the situation where the Orion Nebula glows because there's still plenty of gas. There's still stars being formed, but the stars that have already achieved ignition are now putting out energy that's energizing the gas around them and lighting them up.
Okay.
True of many of the messy objects that we love. It's that they've got somewhere in them, they've got an energizing star. And if we get into if I bring up here the North American Nebula, I think if you look at your next Sky News issue, or maybe it's the current one, I do mention which star is the energizing star for the North American Nebula. And in the issue coming up, I talk about the Fossil Footprint Nebula, and I do mention the igniting star in that one too.
Real quick pitch for Sky News. You get Sky News with your Rask membership. You get 6 issues for the entire year. If you are not already a Rask member, it is a great reason to become a Rask member, but you can also sign up for it without externally from the membership, and there is a website. Okay, sorry, back to you, Chris.
No problem. Yeah, so once you start hitting ignition, then you've got a star. Now, here's a star called HL Tauri, and its protoplanetary disk. This is actually a radio image of it. So by using a large in size and dimension radar dish set, we can produce, using interferometry, these high resolution radar or radio images of various objects in the sky. And so here's an example of comparing the disk of dust and gas around this protostar in comparison to our solar system out to Neptune's orbit. So it sort of gives you a size comparison. Now, what I want to do, here's the picture I was looking for. This is basically all that I've just said in graphical form. So you've got your cold gas collapsing down in stage 1. In stage 2, you get a protostar, and as it contracts, it also decreases in luminosity, drops down, and then eventually resides on the main sequence of stars. So if you think of the protostar as babyhood, infancy, then the main sequence would be the bulk of your life, your up to middle age kind of thing. So let me just bring my notes up here so I can show you some examples of some of these objects. So the star T Tauri, that's about a 2 solar mass star. It's near the Hyades, and I can show you where it is in stellarium here in a bit. Let me just see if I can bring that up. So I know he wants to go and see a very young star. It's very early stages, and just bring my bookmarks in here.
While you're bringing them up, in case folks are unfamiliar with the terminology, when we're talking about star masses, and also a lot of masses, radiuses, and measurements in space of stuff that's out there, we often measure them based on what we know. So when Chris says that's 2 solar masses, it is 2 times the mass of our sun, right? That's what you mean, right, Chris?
Yeah.
Yeah.
Yeah. So let's see. Let me just bring up so if you stay up late enough tonight, the constellation of Taurus will rise in the east. You can see this is about midnight. Got stellarium showing for tonight in the Toronto latitude, but around midnight or after. So just above that big open cluster, that's the face of Taurus, there is an object, a dusty object called NSE1 or T Tauri, the star named T Tauri. And this is one of these extremely young stars. And actually, before the stars really begin to fuse their hydrogen in their core, they can still get very hot, and we can still detect them in infrared. So they're still kind of glowing, but they're just not fusing in the classic sense. Another one I have here, let's see if I can find it, is V. Let me just bring this up. Speaking of the North American Nebula, V1057 Cygni, is it going to come up? There we go.
What a catchy name.
Yeah. So let me just wind this back. So this is tonight around 9 p.m. So you can head out on and look up. So here's the North American Nebula. It's just to give everybody the context. So there's the zenith, the Z, right overhead at about 10 p.m. Here's the star Deneb. And if you're facing basically west, look high in the sky above Deneb. There's a faint glowing patch of sky. That's the North American Nebula. And inside that, you've got this very, very young protostar, still in the process of completing its evolution. This star has done some really dramatic things over the past 50 years or so. It suddenly outburst by five magnitude values, and then it dimmed again. And we're still not quite 100% sure what's going on, but we think it has a companion, and we think that the companion's orbit is playing around with the protostellar disk, and that's helping to occult the main star's visible brightness, things like that. So cool. Stay tuned. This one's in the process of doing its thing. All right, so let's go back here. So next up, we've got the sort of toddler to middle age frame for stars. And the cool thing about this is that some stars are effectively immortal. All right. So you may have heard that red dwarf stars live for such a long time that there's never been any that have reached the end of their life up to this point in the age of the universe. But before I get to that, let's start at the very, very bottom of the food chain, so to speak. So brown dwarf stars. So brown dwarf stars would be ones that are, say, less than about 80% of the sun's mass. So I'm sorry, 0.08. So only about 8% of the sun's mass. So roughly about maybe 13 to 50 times the mass of Jupiter. So you may have heard that people sometimes talk about Jupiter as a failed star. Jupiter would need to be about 75 times more massive for it to be in the range of igniting in hydrogen fusion. So these super Jupiters are not anywhere close to being star. But these little brown dwarf stars, they're very hot. So they're not fusing hydrogen, but they can fuse deuterium, which is a form of the hydrogen atom. They can fuse lithium, and so they can generate heat and energy. They're more visible in the infrared part of the spectrum. The nearest one that we know of that type of star is one called Luhman 16, Luhman 16. It's in the constellation of Vela, which is the southern hemisphere, so we can't see it from here. All right, let's go back to mine.
Would it be visible with the naked eye, or would you have to get a telescope to see it?
No, it would be very dim.
Okay.
Yeah, really dim. So let me just run it back over here to the PowerPoint for a second.
As you do, I will be sending out a link to a talk or a researcher that we had who talked about brown dwarfs. And I understand why you called them the bottom of the list, but I am somewhat offended by it because I like them.
Bottom of the mass ladder. Let's put it that way.
Fair. All right. Fair.
Not least important, not
smallest.
least interesting at all. Just the beginning of the story.
So I will send out that video for anyone else who wants to suddenly gain a very strong opinion about brown dwarfs.
So this is what's going on inside the star. So we've got, when you get to the point where we've got sufficient energy, sufficient density and sufficient pressure in the core of the star, then it's enough to trigger the fusion of the hydrogen atoms. They generate neutrinos. They go through kind of a step-by-step cycle. This is called the cycle. And you produce at the end helium atoms as well as energy. And we've talked about the sun in the past in some of our past sessions about how it takes a long time for that energy to escape out of the sun and that kind of thing. But essentially, you just want to keep this in mind, this picture of the hydrogen fusing into helium. And when that's going on, you create a situation of hydrostatic equilibrium. So the mass of the star wants to collapse on itself, but the fusion energy being released in the core of the star is counteracting that effect. And so the star lives its entire life, basically. It's all its main adult life, if you want to think of it that way, in this balancing act between gravity wanting to crush it and the internal force, internal energy production, keeping it upright, keeping it inflated. And it's at the end of the life when the interior energy production falters that we start getting the fun stuff happening. But this is basically the situation you have, and it really doesn't matter too much about the mass of the star. Any massive star will have this balancing act going on. And so, but what happens at the end of the life depends on the mass of the star. So we'll come back to that in a bit. Let me just bring my notes up here. So yeah, so the core is about 10 million degrees or 10 million Kelvin when it's on the main sequence. Stars that are more massive than our sun, say more than about 1.5 times the mass of our sun, they can also produce energy using another cycle, another fusion process called the CNO cycle, the carbon, nitrogen, oxygen cycle, that also produces energy as well. So let me just show you the family picture here. I love this diagram. And I'll just click on it to make just come up. So we, back in the day at Harvard University, Henrietta Levitz created this classification system that she noted that the spectrum of different stars had an association with their color, their perceived temperature, their brightness, and that kind of thing. And so she produced a spectral classification system. And really, it kind of started out as A, B, C, D, E, but over time, it got rearranged and modified as discoveries were made until we end up with the modern set of letter classifications that you can see here under spectral type, O, B, A, F, G, K, M, and there are lots of mnemonics that people use to remember those. And so you can see here that essentially you've got O stars are the hottest at 40,000 Kelvin. That's their photosphere temperature. So that's the visible surface that we see, the visible temperature, not their cores. They have actually they're much bigger than the sun, maybe 50 times as big as our sun, maybe 100,000 times as much light, but they live for a very short time, only 10 million years, only 10 million years. And that's because they're actually consuming their fuel at a very rapid rate. And I'll circle back to that in a second here. And one of the examples of that type of star is the star Naos. And Naos is in, come back here, I'll find you Naos. My list here. What I might do is save these up and show them later. So Naos is a star in Puppis, which you can see if you stay up late. So it's a hot, very hot blue-white star, one of the hottest stars we know. Then we get to the B star. So now we're kind of white hot here. Now we're getting to the more blue-white, more white. And as you can see, we go into more yellow, orange, and red. So the B stars are a little bit cooler, a little bit smaller, and live a longer time, 100 million years instead of 10. The A stars, cooler yet, live for a longer life cycle. And then we get into the F and the G. So our sun is a G star, kind of peaks in the yellow range of the spectrum. It's got a photosphere temperature of about 5,700 K. And of course, we're using it as our candle, as our measuring yardstick. So it's one solar radius, one mass, one luminosity. And it's going to live for about 10 billion years. So if a typical star lived for 100 years, I think our star would be around 46 years old, if you want to think of it that way.
Right, so like middle-aged.
Middle-aged, yeah. Then you move on, you get into the K stars, which are cooler yet, 4,500, live about 5 times longer. And then we get to the M stars, which are coolest of all, and they live for trillion years, could be up to trillion years. So longer, almost longer than the age of the universe so far. And what the impact of all that is that because the M stars basically never die, they're very abundant. 80% of the stars in the galaxy would be the M stars. But because they're relatively low energy and relatively faint, then they don't dominate our nighttime sky. The ones that dominate our nighttime sky are the big proud O ones, the O and B stars, which are pedal to the metal, putting out all the energy that they can. So here's something cool that I learned about why this is the case. So I thought, I used to just take this as face value that the M stars live a long time, but there's a good reason for that. And what it is that when the star is this small, so you can see that here it's a fraction of the size of our sun, it's less dense in its interior. And when it's less dense, it's more able to mix and convect. The mass can convect and mix around. And so the helium doesn't build up in the core. And so the helium is able to be circulated out of the core and fresh hydrogen brought in. So it kind of is like feeding continuous natural gas to your furnace at home. It never runs out, it never overheats. So the thing that brings most stars to the end of their lives, or at least sets them into a new chapter, is when they exhaust their core hydrogen, then it needs another threshold of pressure in order for the helium to begin to fuse. And so depending on the mass of the star, that happens easily or not. So in an M-class star, that constant mixing means that the core never gets that threshold of depleted hydrogen, increased helium. And so they just keep trucking along for basically forever. So yeah, you can see that the abundance of the O and B stars are fractions of a percent, and then the K and the M stars are the vast majority of the stars. And here I've got samples of all these different types. So as I said, you can go see Naos in Puppis. You've got Sirius, which is going to be up later tonight, but with us all winter long, and Procyon. So those are your A and F stars. Capella is already rising in late evening now. So Capella is somewhat sun-like in its type. Then we have Aldebaran, which is again in Taurus, which rises in late evening. And then the Barnard star is actually in Ophiuchus. So it's available right now in the evening. Let's see if I can find Barnard star for you. So here we go. So Barnard star, let's put this aside a little bit so everybody can see. So if you look at the southwestern sky around 10 p.m., you can see there's the sort of Dalek shape of Ophiuchus. He's got his kind of, some people call this group of stars his pipe sticking out, and Barnard star is this neat little red M-class star sitting here. And we've talked about this before, where if I center on another star and I advance, Barnard star is a high proper motion. So every year it moves across the sky. So it's a cool project to image that patch of sky and see Barnard star as it moves around.
Cool.
Yeah. So you can head on out and look for these kind of main stars, main types of each category of star. And then we've got these other types of stars that are not your main sequence, regular middle-aged stars. You've got giant stars, white dwarf, and supergiant stars, and we'll kind of come back to some of these in a bit here.
Wait, hold on. Can you sit back for a quick second? Because I have one question just quickly about like the casual names of all of these things that people, because I'm used to hearing things like red dwarf. Is Barnard star is a red dwarf, yes?
Yeah.
Yeah?
Yeah.
And then our
sun
is like boring, not boring.
It's a main sequence star. So these would all be called main sequence stars.
Okay.
Except that you can have names like blue giant, but blue giant is not astrophysically a particular star, a physical property. It's a descriptive nickname rather than actual a type. Whereas a red dwarf is adopted by astrophysicists to describe that type of star.
Okay.
So yeah, main sequence stars are the ones that are just doing their thing in middle age, up to middle age. And then the names like red giant, supergiant, white dwarf, those are the products at the end of the life, generally in the dying stages of life or at the end of star's life. Yeah.
Okay.
So good question.
And then one more question from Cicely. I don't know the answer, so I always hesitate asking questions where I don't know the answer. According to the song, I don't know the song, but apparently there's a song out there that says the sun is a massive incandescent gas. Is this true, or do the lyrics need updating to fusion frenzied plasma?
Updated to fusion which?
Fusion frenzied plasma.
Fusion frenzied plasma.
It won't rhyme.
Well,
but will it be accurate?
Well, that's the key, is that we don't see the fusion happening. The fusion's happening in the core. We just see the end result. So what we're seeing a lot of is the ionized composition, the stuff the star is made of when we look at a star. So.
Okay. All right. I think that's an acceptable enough answer.
So what are the options again? Give me the options again.
Either incandescent gas.
Yeah.
Which is technically true. Or fusion frenzied plasma. And the wording here is the sun is a mass of incandescent gas. So it's not necessarily what we can see, but what it actually is.
Yeah. I think incandescent gas is reasonable to say, except it only applies to the outside. I don't think it applies. So what you're saying is describing two different parts of the star, in my opinion.
That's fair. Cicely, you need to please update the song and get back to us. Thank you.
All right, let's see if there's anything else in here I want to mention. Yeah, I think that's it. So things go along for a good while. I'll go back to my HR diagram here just to set the stage so everybody can see what's happening here. So the stars that are on this diagonal strip here. So down here across the bottom, we've got those stellar classification letters that I talked about a minute ago. So the stars to the left of the graph will be the hottest, whitest, bluest stars. The ones in the middle will be the warm colored stars. And then the ones to the far right will be the dim reddish stars. And below that, you can see the temperature, the rough temperature ranges that go with that. Then the vertical axis of this diagram is luminosity, so how bright the star is. And generally speaking, as I said, the red dwarf stars are the dim, cooler ones, and the hot O stars, like Naos, are the bright and hot stars. So they dominate the sky. So when you look at Vega and Deneb and Altair and Orion's Belt and all of those sort of big in-your-face stars that we're used to seeing in the sky, those are typically the O and B and A extra bright stars. And ironically, they're the shortest lived. So our ancestors, our ancestors long from now might see different star patterns because the dominant stars that we have right now will die out. So everything sort of sits here in the main sequence for the bulk of its life, and then when the things start happening in the core and the end of life begins to happen, that's when they start diverging off and evolving into different regions of this diagram. So essentially, the kind of rule of thumb is that things either cool, so they swing to the right, and they tend to swell up and emit a bit more light, so they kind of do this red giant thing. And this is actually the red giant asymptote. There's a curve here that's followed. And then for a while, they do some other activities I'll get into in a bit, where they sort of slide to the left for a while. And then at the end of the process, they all basically end up dropping their outer shells out and revealing their cores as white dwarf stars. And that's why the white dwarf stars are kind of hot, but not as bright because they're not as big, and they sit here at the bottom of the diagram. So that's sort of kind of rule of thumb. All right, let's go back to the notes here. So what happens basically depends on the mass of the star, and the little 10% mass of stars, 10% solar mass stars live for a long time. They have that core, that fluffiness that allows them to do all that mixing, lots of population. And they can actually eventually evolve into white dwarfs. So essentially what happens is that the outer skin of the red dwarf star begins to become increasingly opaque, because as the hydrogen in their envelopes build up, the doubly ionized hydrogen becomes opaque to light and opaque to radiation, and it actually locks the heat inside the star. So that causes them to heat up, and eventually they can become, a lot of the times they become a blue dwarf, and then the blue dwarf then completely runs out of fuel, and you end up just with the core cooling down. So white dwarf star is not fusing any hydrogen, it's not doing any fusing. It's just a cooling ember, if you want to think of it that way. Of the red dwarf end-of-life stars that we know of, there's one called Lalande 21185, and that's in Ursa Major. I'm not sure if I'll show that in a bit here. And Proxima Centauri, everybody's heard of Alpha Centauri, Beta Centauri. Proxima Centauri is the third sibling of the family. It's the little red dwarf star that's actually technically the closest to Earth of the three. It's 4.2 light years away from us. Can't see it from Canada, though. Actually, it's hard to see even when you're in the southern hemisphere, because Proxima is really dim, really faint. I think it's probably magnitude 13, 14, something really dim.
Ooh, so you need like a big telescope.
Yeah. We can look it up if somebody's really keen to know. All right. So now that's dealt with the lightweight stars, the low mass stars. Most stars that we're familiar with, though, are the kind of middle range mass stars, sort of between 60% of the sun's mass and 10 times the sun's mass. And those are those ones that are on the main sequence here. And you can see the lifetimes as well in the diagram here. Now, things are going along great for a long time. And then when things start going bad is when the hydrogen fusion in the core ceases. So when that happens, that balance of pressure that we talked about can no longer be sustained, and the star immediately wants to contract. And depending on the mass of the star, a few different things can happen. So in one situation, the star contracts, the pressure inside the star increases to a point where there's enough density that the helium can begin to fuse. And so the star gets a second start on life. And when that's happening, you've got a core that's fusing helium predominantly, but then you've still got a shell around the core where there's enough pressure for hydrogen to fuse. So you've got this sort of twin furnace situation happening. And that shell of hydrogen around the core, which is not really constrained by very much pressure, that's what causes the star to swell up. So that heating of that hydrogen shell around the core causes the star to swell up, and that becomes a subgiant star. So that's where you're seeing kind of in this little lower branch of the main sequence here. So subgiant stars would include the star Alshane, which is Beta Aquilae, and Algenib, which is Gamma Pegasi. So let's just look at a couple of those. So where we've got over here in Pegasus, we have Algenib. So that's one of those subgiant stars. It's evolved in its life. And then we're back in Aquila. We have Algenib. I think that's, no, I think it's, which one is it? Alshane, that's the one. Subgiant star.
Both of those are really easy to find, and I'm pretty sure both are also visible from the city, which is nice.
Yeah. So as things are going along, then eventually the kind of outer layers of the star will cool down. And if that sort of outer layer becomes opaque enough, then the heat is trapped inside the star, and the star begins to expand and heat up even further. And that's where you get into the red giant situation here. So now we're talking about Aldebaran, Arcturus, Betelgeuse, things like that. So you're getting to that end of life. All right, so let's talk a bit about pulsations. So while that helium is being fused in the core, there's kind of a dynamic energy transfer happening inside the star. So you've got a source of energy in the core, you've got a source of energy in the shell, kind of in the intermediate layers of the star. And so you can end up with a situation where you've got pulsations going on. Because the helium that's being produced in that shell of hydrogen around the core, it sinks into the middle and it sort of adds to the mix. And so you get these pulses of energy, and that's where Cepheid variable stars come into play. So that's what they are. They're in that process. So let me just bring up my stellarium and show everybody some Cepheid variable stars. So these stars are in the kind of 4 times the mass of the sun to about 20 times the mass of the sun. And that idea of the doubly ionized helium on the outer skin is holding the heat in for a while. That causes the star to swell up, and then it cools down, dims again. So that cycle gives you that sinusoidal brightness and dimming all the time. So Eta Aquilae is one of those classic Cepheid variable stars. So this one actually varies by about double its brightness. So it changes by 1 integer magnitude amount from 3.5 to 4.5 every 6 days or so. One thing that I found out in Stellarium is that it's now reporting its next minimum brightness.
Cool.
So for some of these variable stars, you can now see the next reported minimum. So that's cool. If you do look at the star on the next clear night, what you can do is you can compare it with the tail of Aquila down here and this little star Iota between them. And so when it's at its minimum brightness, it's the same as Iota. And when it's at its maximum, it's the same as the tail. So these 3 stars. And this is the Cepheid variable star. Another one is Delta Cephei. So here's the upside down house of Cepheus. And if you look at the upper right corner, so the corner above Cassiopeia, sort of between Deneb and Cassiopeia, that's Zeta. Zoom in a little bit here. So there's Delta Cephei. Again, Stellarium says the next minimum for Delta Cephei is September 30th at 23:05. So that's UT. So that's 7 p.m. in Toronto. But, keep an eye. And essentially, you've got this trio of stars, Delta, Zeta, and Epsilon. This one also varies by 1 magnitude about every, I think it's about 5.3 days. When it's at its brightest, it's the same as Zeta. And when it's at its minimum, it's the same as Epsilon. So just head out. You don't even need binoculars, but it helps if you have them. But if you've got good eyes, you can see this little trio. You can then judge where in the cycle the Cepheid variable star is. So let's talk about carbon stars. I love carbon stars. I don't know about you, but when you're in the neighborhood, take a look at the Garnet star. The Garnet star is a naked eye star. It's easy to find because it sits above and between the edge of the box of Cepheus. And man, oh man, this star is unbelievable. It's, I don't have all the facts and figures in front of me, but it's a couple of thousand times the mass of the sun, puts out so much light, almost, I don't know, a distance of almost 6,000 light years. The fact that it's a naked eye star at almost 6,000 light years just tells you how much luminosity it puts out. And it's really, really red in the eyepiece, especially compared to the stars around it. So what's going on in these carbon stars? So the convection that's happening in the evolved star lifts, so we've got helium producing carbon in the center of the star now in the core. And in the stars that are able to convect in their envelopes, the sooty carbon can get lifted to the surface of the star, and that can then scatter the blue and green wavelengths of light and leave the reds and oranges. And that's what you're seeing in those so-called red carbon stars. And you can find lists of red carbon stars, in viewing guides and things like that. I've got a few here listed. Let's see if we can find a couple for you. So there's the Garnet star, which is easy. You don't need binoculars. You can just look for the box and Cepheus and see it glowing faintly red right above it. U Cygni, where's my U Cygni here? U Cygni. So that one's located. So there's Deneb, there's Alberio, and U Cygni is kind of in this corner. So that's a reddish, really red star. TX Piscium. TX Piscium.
U Cygni would be a lot dimmer too.
Yeah, it's magnitude 8, so you'll need binoculars for that one, or your telescope. T Lyrae. So there's actually a couple here in Lyra. So you're looking at, there's Vega, there's the double. So these are about finger's width apart. And you're looking on the opposite side from the double, and there's, let's see, there are 2 of them in here. I can't remember the other one right now, but yeah, it's a great pulsating variable carbon star, magnitude 7.5. So binoculars would pick it up, but a telescope would work even better. All right. So then after this pulsating goes on and things are going a little bit crazy, that's when you get to the process where the outer shell, there's enough energy being created in that shell around the core that it can blow off the outer layer of the star. The helium process, the helium fusion ceases in the core of the star. The core collapses, everything rebounds, and it blows off the outer envelope of the star and produces this.
Hey!
Planetary nebula. So planetary nebulas are all over the place in the sky. I've got a really neat picture here I'm just going to bring up, showing planetary nebulae. Kind of a family of pictures. We'll just do this.
Oh, look at them all. They're all so cool. Yeah,
so the detailed manner in which the envelope gets blown off and the metallicity or the composition of the star will control the shape and the colors and the various gases that give you the different ionizations of the different colors. And what's cool is that I have names on these. I don't know if you can see them
Wow.
all, but I think these are to scale. I think they are.
That's really cool.
I'm not sure if these are to scale or not. I think they might be.
They
Yeah,
are
so
they are
there's
super tiny. Like
yeah.
they're like quite small.
Yeah. So you'll need to use your maximum magnitude eyepiece on these generally.
I'm also going to throw in, so for those who don't know, I'm a marine biologist, and these remind me a lot of diatoms. If anyone knows what diatoms are, they're like small algal species that have just really varied, often quite circular outer shells almost. And I don't know. I love them. It feels like you're collecting Pokemon when you find them. I don't know. That's how I feel about it.
Yeah, they're really fun. And what's great is that we're very lucky to have some very accessible ones. We've got the Dumbbell Nebula and the Ring Nebula, which are sufficiently bright for most inexperienced observers to see them clearly in a telescope, say at a star party or that kind of thing. And if you take long exposure photographs, you can start picking up some of the variety in the colors. There's the Dumbbell Nebula. The Dumbbell Nebula itself is quite a bit bigger than the Ring Nebula. So it almost looks like an apple core, an eaten apple core when you see it. And it's visible right now in the evening sky in the area near Cygnus. We've also got near the upper wing of Cygnus, we've got the blinking Planetary Nebula. This one you generally don't see much structure when you're looking at it through your telescope, a backyard telescope. But what this one does is it has a very prominent white dwarf star in the middle. So that when that outer shell blows off, the core of the former star now becomes a white dwarf. It's basically a very hot ember that will cool over many, many thousands to even a million years. And when you're looking at a planetary nebula, you can almost or very often see the little white dwarf star in the center that's producing the glow in the gas around it. And if you look at the planetary nebula, the blinking planetary, if you look straight at the white dwarf, it'll be prominent and the envelope will dim. And if you look away, then the envelope will brighten up. And you can go bright, dim, bright, dim, bright, dim by using your averted vision to look at it.
That's why it's called the blinking one.
That's why it's called the blinking, yeah. Another really good one is let's see if I have the helix. Should be down here somewhere.
Oh, sorry. As you find it, I'll look for something else. We have data from our robotic telescope in California of the Helix Nebula, and it is free to play with if you want to try editing astrophotos. So I'll see if I can find a link to send out.
So as most people know, objects look their best when they're highest in the sky because then you're viewing them through less of Earth's intervening atmosphere. Unfortunately for us, the helix is relatively south in the sky. So here in Canada, it doesn't climb that high for us. And it tends to get overlooked, I think, because it's maybe because of that, or maybe because it's not quite as bright, but it is absolutely spectacular. It looks a bit like the Ring Nebula, but it's much, much bigger. So I think let's see, this one is it's a size of 25 arc minutes by 13, almost as big as the full moon.
It's huge.
It's really big. And so if you've got a nice dark site and you wait till it's culminating and it's nice and high. So right now it's culminating, let's see, around 11 o'clock. Really try it. It's well worth it. It's really a nice object, the Helix Nebula. And it's a real favorite for imagers too, because it's one of the bigger planetaries, and imagers like objects that have a bigger scale to them. Mm-hmm. All right.
We have, if you're at a good breaking point, we have a couple questions, one that I slacked on asking and was relevant like 10 minutes ago, and one that needs its own little sort of gap to fill. Is now a good time, or is later better? Okay, so the first question is regarding the Garnet star. I can't remember what you said. You said it was like 6,000 light years away. Is it near the outer edge of our galaxy? Do you know?
I'm not sure. I haven't thought about it in that respect.
Yeah, I guess we often don't think about where stars are in 3D space. We just think about how far away they are from us. I'm not sure.
Well, the galaxy it's near the plane of the galaxy, so it's in the disk close to the disk of our galaxy. I don't know if you noticed that Let me see if I can, I'll just go back there for a second here. So there's the winter Milky Way stretching up right here.
Yeah.
So that's the plane of our galaxy. So it's within the plane of our galaxy, which gives us lots of real estate to play with, because the outer rim of the galaxy is down near kind of Perseus region. But we're kind of in the middle of the disk. So we've got 30,000 light years towards the core, and we've got another 20 or 30 light years to the outer rim. So yeah, it's
20 or 30,000
kind of
light
in the
years, or
plane.
20? Yeah. Yeah. And then another question, which we have talked about before, and I never have a good answer to it. Are there absolutely no green stars? I have an idea why, but I can never explain it. Can you explain about why there are no green stars?
It's because the graph of wavelength versus light production from a star, and that black body curve, is flat near the peak.
Right.
So
the
even
light
though
is spread out.
Yeah, well, it's like, because it's so flat, even though green might be slightly more energy than the yellow beside it, it's not enough to completely overwhelm the light we see from it. So it's partly a perception. Our eyes are tuned more to yellow, the wavelength of our sun's light, the kind of the whitish yellowish light. So whereas a red dwarf star or a carbon star, their light peak is really shifted over to the red part of the visual spectrum. So and the blue is the same at the other end. But because the yellow and the green are kind of in the middle of the range, there's little difference between those wavelengths in terms of energy output.
And I guess it's, since the visible part of the spectrum is only a very small part, and then there's ultraviolet on one side and infrared on the other, you can get a lot of light shifted to one side or the other. But yeah, no matter what, since it's the light is spread out across multiple wavelengths, and so like a large section of that graph, if you had it on green, it's taking up almost all of the visible light. So it just appears white because there's still light being produced in blue and red. Yeah?
I think so. I can look into it a little bit more and can talk about it on a future session.
Okay.
But that was the kind of the impression that I had.
Maybe we can do like a pop science version of of this show, because there's a lot of really like popular questions out there, like does Jupiter protect us from asteroids and stuff like that. When we do a pop science episode.
Sure. Was there another question, or those are the two? Those
are the
were
two. Yeah.
One final thought on white dwarfs, just before we move on. So the white dwarfs are very, very dense, right? They're about 0.6 solar masses compressed into a volume of the size of the Earth. That's how dense they are. It's about 1.10 to the 9 kilograms per cubic meter of mass. Extremely dense. Another example of an observable white dwarf that is not in a planetary nebula is the Sirius B, the partner to the star Sirius, or Sirius B. I've seen it visually in a big telescope under good sky conditions. It's a little bit of a challenge. It's not as close to Sirius as I thought it would be, but it's so overwhelmed by Sirius's brightness that it's tricky to find it. All right, so let's talk about what happens in big, massive stars. So sort of more than 40 times the mass of the sun. Go back to our HR diagram. Come up with this here. All right. So the higher mass stars, they're already more massive and brighter. Anyway, these are stars like, as we said, Deneb, Bellatrix, Rigel, Spica. They're usually the O and B type stars. If you look at the constellation Perseus, the brightest star in Perseus is Murphak, and in binoculars, it has a spectacular array of O and B stars surrounding it in a clump. So the B star, these more massive stars, like the blue giants, they have more opportunity to continue burning even once the core hydrogen is exhausted. They start to consume their core helium and begin to fuse some heavier elements. And they do that even though they're hotter, they're actually able to maintain their luminosity. So they kind of spend, once they evolve off the main sequence and their cores begin to fuse the helium, they're able to sort of maintain a constant luminosity as they migrate kind of to the left here above the main sequence of the stars. So they can go through stages where they're blue giants, bright blue giants. They could even become yellow supergiants, and then eventually red supergiant stars. Now, the stars that are heavier than about 8 times the mass of the sun, those cores can actually fuse the helium into heavier elements like the carbon and the oxygen, sometimes neon. And if the star is sufficiently massive, then even the carbon can begin to fuse in the core, and it'll turn into heavier elements yet. So that's where you get the oxygen, the silicon. And the end of the process is the iron. When the iron atoms begin to be produced or generated in the core of the star, that's the end of the line, because the iron is a net receiver of energy rather than a net producer of energy. So once you start accumulating iron in the core of a star, that's going to be the end of the life of the star, because it can no longer produce energy in the core and hold itself up over the gravitational collapse. So you can think of all of that what I've just said in kind of an onion sense, where you've got you'll have an iron in the very core, then you're going to have your silicon shell, an oxygen shell, a carbon shell, and then on the outside of all that, you've still got hydrogen fusing in a shell around the outside, and then the rest of the star as well. So when the the amount of iron accumulating in the core reaches about 1.4 to 1.8 times the mass of our sun, the equivalent to that. And don't forget, we're talking about a star that starts out as already about 40 times bigger than the sun anyway as well. That's when you will reach what you may have heard of as the Chandrasekhar mass limit. And that's at the point where the fusion has to stop. And that's when the core basically becomes dead and collapses, destroying the star. And that's when you get a supernova. And the result of the supernova, in addition to the supernova, you'll produce the core will remain behind after the supernova as either a neutron star or a black hole, depending on the mass of the star. So let's talk about some examples of that. So the last time we had a supernova happen inside our own galaxy was the year 1604, and that's what's known as Kepler's supernova. The star named, the remnant name now, is V843 Ophiuchi. I don't know if I've got it in here. Let's see if I do. I have Kepler's. Here we go. I'll show you where it is.
Where's the universe going?
Where we go? What happened? I'm too big. Here we go.
Oh, it's mostly up in the daytime, I guess, eh?
Try that one more time.
Aha.
There it is. There it is. I was zoomed in too much on the Helix Nebula or something. So it's actually sitting here in the leg of Ophiuchus. So it's a bit, rather low on the horizon for us to see it. Actually, it's represented now by a dim double star, so it's not going to be much to look at. But that's basically the last one. So that's about, the last one we had was 400 years ago. They're not very common within a galaxy, but thank goodness there are loads of galaxies in the sky. So supernovas are observed going off all the time. So what I did is I gave Jenna here a tab. You can see that tab.
Oh,
Let's
yeah.
open this up. Let's open this up and bring it over. Here we go. So somebody has done a nice job of tabulating the latest supernova that occur. And here's the list that was updated on the September 28th at 11:20, and so on. So the current one that's going on right now is 2021 SMJ, which is a 13.6 magnitude type 1A supernova in the galaxy NGC 4411b. So I've got that in here. I'll show you where that is. I think I've got that set up. NGC 4411b.
Oh, I see it. It's 3 down from there.
Yeah. There we go. So this one's actually in Virgo cluster, not visible right now. The next one was 2021 WUF. That should be in here as well.
What was the name again?
It's 2021 WUF. Thought I had it in here, but maybe I don't. I know this one is observable. Did I put it in? That's okay. I'll look it up after. I can chase it down afterwards. So a high mass star, just go back to something in the neighborhood. Here we go. Back to tonight. So if I go ahead.
Cicely found it. It's second from the top. It's just that 2020.
There you go. Head in the wrong
you,
category.
Cicely.
Here we go. Where is it? NGC and okay, I'll do it this way. NGC 65.
Be careful, it's not typing in, it's just removing all of your extra stuff.
NGC.
You gotta type the name backwards to get your stuff back. Yeah.
There we go. It's at the top of Ophiuchus. Everything seems to be in Ophiuchus these days.
It's a place to be.
So that's where there's a supernova happening right now. I will remind people that are using Stellarium that if you don't see anything going on your screen, go down and make sure you've got your DSS, Digital Sky Survey tab enabled, and it'll go off and it'll grab images for the sky. Here we go. So that's the galaxy it's happening in right now.
Cool. I'm going to take a quick second while we're talking about supernovae and other galaxies to mention as well that in the next few months or so last month we ran a science processing course about how to find exoplanet transits. And in the next few months, we're going to be running one about how to find supernovae in distant galaxies. So stay tuned on the RASC website for that.
Cool. Okay, so now we're into the fun stuff. So these big massive stars, more than 40 solar masses, they reach the end of their lives, they collapse, they blow up, they end up with a supernova happening. So that could be a type 1b, a type 1c, a type 2 supernova, plus either a neutron star or a black hole. The mass cutoff that decides that is dictated by the mass of the star to begin with. So if it's about a 10 to 25 times the mass of our sun star to start with, then it'll produce a core that's about 1.5 to 3 times the mass of our sun, just the core. And that'll give you a neutron star. And over that, roughly, it'll give you a black hole. And it's, if you want to do some reading, there's a limit. The limit's called the Tolman-Oppenheimer-Volkov limit that's based on the calculation of degeneracy and the density of the neutron star. And there is some wiggle room that's in there based on the metallicity. So the metallicity of a star is how much of elements higher than helium does the star contain. So other trace elements if you want. So that's what you get that. And if you have, you end up with that white dwarf being that sort of exposed core of the former star. If that white dwarf star has a binary companion, binary partner, which is able to supply hydrogen to it, then that can produce a recurrent nova situation or a cataclysmic variable star. So essentially, a white dwarf star can just live the rest of its retirement, or if it has a partner able to feed it a steady supply of hydrogen, that can accumulate on its surface. And when it hits a threshold, it'll flare, and that'll produce a nova. And that's what that star RS Ophiuchi did, which is down in here a couple of months ago.
Yeah,
First time in 16 years. And it can happen periodically as the hydrogen's coming off the partner. So that can be a situation where you have a white dwarf and then a partner star. The star swells up into a red giant. That means the star envelope is close enough to the white dwarf to start getting material drawn off, and you get that situation happening. So that's what happens with the white dwarf. If you've got a star that produces the neutron star, so in a situation where we have the neutron star essentially is degenerate, where the electrons and the protons are pressed together to form neutrons, and you end up with a sphere of neutron, essentially solid neutrons. As the star collapses in radius, reduces in radius, it spins. And that's where we get our friend, the Crab Nebula.
Yay!
So the Crab Nebula was observed as a supernova in July of 1054 by the Chinese astronomers. It was bright enough to see in the daytime for a number of days. Then it faded in brightness. It became the dominant object in the night sky for a number of weeks. And then now, 1,000 years later, we had the remnant of the still expanding shell of the former star expanding around. And in the center, we have basically a radio beacon, a rotating, a spinning neutron star producing what's called a pulsar. And I think that's 33 milliseconds. Every 33 milliseconds, a beam of radio sweeps past us that we can detect in our radio telescopes. And that's basically just conservation of angular momentum. It was rotating slowly, but as it shrunk, it sped up. And now it's really fast.
Can I steal the first of all, I think astute observation from Dan Hallett, who says that the Crab Nebula is behind you, isn't it?
Yes, it is.
Yeah. Okay. And can I steal screen sharing for a second to share my all-time favorite image, which is a time lapse of the Crab Nebula?
Take it away.
Yay. Okay. Sorry. Hold on. It'll be real quick. But here's a GIF. Oh no. Of course, it stopped playing.
I know. I love this.
Yeah, of the Crab Nebula over. I think this was over 10 years or something like that. But you can see. It's just so cool. You can see it expanding compared to the stars behind it, and you can see the pulsar like sending out waves. I think. I don't know. It's just so cool.
So I'm gonna do you one better here.
Oh, okay.
Or as good. So I've discovered this video today. This is a YouTube video by Adam Block of the pulsar inside the Crab Nebula blinking.
Oh, that's cool.
So there's a light flash in addition to the radio flash.
That's very cool.
Yeah. So that's cool.
All right. Also cool. Time lapses of astronomical objects, everybody. If you have cool ones that you want to share, send them in the chat.
It's what's great is that as time goes on, we'll have a longer and longer time window to record the 4D astronomy. So it changes over time.
So cool.
Just a point to give credit where credit is due, right? So the first pulsar discovered was by Dame Jocelyn Bell back in, it's in August 6th of 1967, the summer of love. And at first, her supervisor thought that this fluctuating signal, what must have been noise. She built the radio telescope, and it was her radio telescope picked up the signal. But then she managed to persuade him that it was a genuine signal. They actually discovered, originally they called it Little Green Men, LGM is the name of the pulsar, but it's been renamed now. So it's now named is PSR J1921 plus 2153. And those latter numbers are its coordinates in the sky. And if you're interested in seeing where that is. Oops, why didn't it go? Let's see if it's maybe my stellarium has decided to stop cooperating. It is maybe. Try one more time. There we go.
No,
Doesn't want to cooperate. That's okay. It's right where it is. It's in Vulpecula. It's near NGC 6793. So let's do it that way. NGC 6793. So it's in this region of the sky. If you're interested in kind of gazing in that direction and appreciating Dame Jocelyn Bell, that's where it is. And of course, we've discovered many, many of them since. The map of the vectors that were put on the golden record that was on the Voyager spacecraft was a map to various local pulsars that will help aliens find Earth, find the sun in some future time. All right, coming up to the end, the more extreme case is that if a star began at more than 40 times the mass of the sun, it's going to have a correspondingly much bigger core. And when that core fusion ceases, it's going to be about 2 or 3 times the mass of the sun, the core itself, and it's going to collapse and gravity is going to just take over. And that's when you're going to get the black hole forming. And it's in my reading, I read that we're not quite sure whether you need to have a supernova to produce a stellar mass black hole. And then we're also not sure whether a neutron star could at some point continue to collapse and transform into a black hole. So those are some unanswered questions about stellar mass black holes. If you want to see the black hole, the first confirmed black hole, that's in the neck of Cygnus the Swan. That's Cygnus X1. Let's see if we can pick that one up. Now I'm just going to go there because I know where it is. So this is one you can see for yourself. I've done this with my telescope. So if you look at Deneb and then the Saturn star and then Albireo, which is the long neck, about halfway along the neck of the Swan, you've got a visible, it's a naked eye star named Eta Cygni. And then there's a little nebula here, which is hard to see in a backyard telescope, but you can definitely see Eta. It's an easy star. And what you're going to look for is the 1357 Cygni. And that's a blue giant star. And back in 1971, the astronomers using sounding rockets detected an X-ray source in this patch of the sky. And Tom Bolton at the University of Toronto decided to use the David Dunlap Observatory's 74-inch telescope to take spectra of the stars in that vicinity. And he found this blue giant star whose spectrum was Doppler shifting blue and red back and forth on the order of several days. And so he deduced that something was tugging the star around, something invisible, something producing X-rays, something that was more massive than the blue giant star, ergo black hole. So you can find this magnitude 8.8 star and know that there's a black hole tugging that star around. Let me just, I'll put up the, put on a circular field of view. Let's see if I do a 1 degree. How much field of view will that be? So there's a 1 degree field of view in your backyard telescope. So you should be able to put Eta near one edge and find V1357. Well, you can use, you can certainly use some star patterns to find it. So you too can look at the supernova remnant. Now to finish up, let's finish up with some exciting objects, and those are supernova remnants. I'm just going to change this back to binocular size. There we go.
Just to acknowledge the questions, we do have some questions that are waiting to be answered, and I will ask them at the very end because I have fallen behind. And almost all of them are from previous topics. So we will wrap it up at the end.
Okay, yeah, I'll go through these relatively quickly. So supernovas leave evidence that they're traced behind. One of the most famous and accessible to folks in Canada in the summertime, in the late summer, early fall, is the Veil Nebula or Cygnus Loop. So we think this is a ragged, roughly circular supernova remnant. It happened about between 3,000 and 6,000 years ago. We're not quite sure. It's about 1,400 and 1,500 light years away from us. You can see that these are binoculars. This circle is binoculars. So that's several times the diameter of the full moon. My trick for finding this, it's my dead easy trick, is to look for the bright star 52 Cygni. That's a naked eye star. You could manually point your telescope at it and then look for a bright streak of light passing through the eyepiece. If you've got an oxygen 3 filter or an ultra high contrast narrowband filter, you can really make this pop. And once you've seen that, you can see there's sort of a curve to it, and you can use that to guide you across and see the other side, the other half. So that's a supernova remnant. Here's another one, Sharpless 2-91. Where do I have this one? Another good one. I wanted to have these in order, but I didn't get to do that in time. Okay, let's go to the Witch Head. So the Witch Head Nebula won't be up until late tonight, so it doesn't rise until after midnight, but it'll be with us all winter. It sits here near M42, the Orion Nebula. It's faint, but it's thought to be a remnant of a supernova. It's being illuminated. It's kind of like a reflection nebula. It's sort of acting a bit like a reflection nebula where it's being illuminated by the energy from Rigel and other stars nearby. So that one is about 900 light years away. And then when you're in the neighborhood, I don't know if you've seen Barnard's Loop. Let me just open up my picture of Barnard's Loop here and show that one. So if you take Orion, there's Orion's belt, there's M42, there's the Witch's Head that I was just showing you, and then there's Rigel, there's Betelgeuse, and there's a very faint ghostly arc of glowing hydrogen gas, which is thought to be a supernova remnant as well of something that happened in the center of the ring. Maybe 2 million years ago. There's various information about that. It's had plenty of time to kind of expand as a shock wave. So that's a cool one. That's a great one for imagers, especially wide field imagers from a dark sky site.
Yeah, it blows my mind that all that stuff is in around Orion and we just can't see it because our eyes can't be open long enough to catch all the photons.
All right, so another one I really like is, let's see if I can find this one. Okay, talk to any links. Chad. Where is it here? Let's do this. Let's do it this way. Sharpless 291. So we'll go back to Albireo for a second here. Go back to this evening. There's another supernova remnant just above Albireo, just a little bit down the neck of the Swan. So if you can find the star 9 Cygni and the star 5 Cygni, and again, switch on your deep sky image. Can you see that there's a little faint streak? There we go, running through here.
Oh, yeah.
And that's the curved edge of a supernova remnant as well. And then I'll finish up with one more, and that is the Spaghetti Nebula.
Delicious.
I have to spell spaghetti right if I want this to work. Here we go. Spaghetti Nebula.
Oh, wow.
So this is awesome. I discovered this, I think I was doing the sky this month for RAS Toronto Center. And here's the constellation of Auriga. Okay, and here's Orion's club, and here's Taurus on to the right. And you can see the star Elnath. And hidden, very dim, is this big, crazy remnant. I'm going to open up. Whoops. Ignore this. Open up the hyperlink. I'll show you a nice picture of it from the astronomy picture of the day. There we go.
That's beautiful. Wow.
Spaghetti Nebula. So I think that's the star Alnath there on the edge. So it's very close to that. And then you can see from the Stellarium binoculars that it's huge. It's probably about 4 degrees diameter in the sky. So I try not to be, academically too rigorous today, but hopefully I've inspired you to do a little more reading and go out and look at some of these various objects and just enjoy the different variety of things to see.
It's
so
really
what are your
neat
questions?
to have, yeah, I was just going to wrap up and say it's really neat to have different ways to look at the sky. You can look at the sky in terms of how far away things are from us. You can look at it in terms of what stage all the stars that you're looking at are at. There's just so many cool ways to explore. So thank you very much, Chris, for doing all that research and sharing it all with us. So we have a couple questions over time that have accumulated.
Okay.
Some of them we might need to just do a whole separate session on because they're really big questions. Starting off, there were 2 questions about iron. First off, is iron the limit? Like, is that the limit of what stars can make, or can they make heavier stuff than iron?
So that's a great question. So the basic idea is, and we learn more and more all the time, but the basic idea is that the regular core fusion process stops at iron. Anything lighter than iron, anything basically between hydrogen and iron can be created in the core of the star through fusion, depending on the mass of the star. You need a massive star to make the heavier. Then during the collapse, rebound, supernova process, those violent events can produce heavier elements. And that's the idea you've heard of about being star stuff and seeding the universe. So the picture of the Crab Nebulae behind me, that's producing heavier elements. That violent explosion produce heavier elements.
So things like gold are only on the Earth as items that as elements that have been created after a star has exploded.
Yeah. So the supernovae, they blast the material into space. It eventually mixes in with the interstellar medium, and then it gets incorporated into a future hydrogen cloud that collapses to produce a solar system, and the cycle continues.
Okay, awesome.
Yeah.
On that note, 2 other questions somewhat relevant. One, I think we're going to have to do a whole other episode on. Why isn't the universe uniform? How come some matter is clumping together, and especially after the Big Bang, how come some matter clumped together?
Oh, you have to read. Yeah. Katie Mack covers this in her book. So it doesn't spend a lot of time on it, but she does cover it a little bit. So it's generally part of most intro cosmology books. It's really fluctuations. So there's so much time for things to happen that any little tiny tip, the dominoes just cascade over time. So really any minor non-uniformity in the Big Bang at the beginning then ultimately ends up with some inhomogeneity.
Right. If you've ever seen someone lying out a whole bunch of magnets evenly on the floor and then flicking one of them and then they all just go, blah! I feel like that appropriately represents matter coming together in a way. Okay. Another question about iron. What size stars give us the iron meteorites that reach Earth? I'm not sure. Yeah, I guess they would have to come from a star, right?
Yeah. So the element iron, which is, based on what I've been saying today, if you look at the abundance of the different elements on the periodic table, hydrogen is first, then helium, and so on. In fact, I think I even have a graph here that shows this. And if I'm lucky, it's here. Here we go. And I'll do this. Oh, where'd it go? Here we go. And I'll share this. So these are kind of elemental abundances. Hydrogen and helium are the most. Lithium is low because it doesn't survive long. And then you get your carbon and your oxygen, your neon, your silicon, and your iron, because those are made in stars and in a lot of stars. And then the other ones are less frequent, they're lower on the graph. The graph goes lower because this is logarithmic. So every step is 10 times less. So these are much more less abundant because they're only produced in supernovas or maybe black hole mergers or some other exotic thing. Mm-hmm. So the irons that we have in our meteorites, it's the same iron that we find in our iron mines. It's just that the iron in our mines got incorporated when the Earth was formed, whereas the iron in the meteorites never got incorporated into a planet. Or maybe it was incorporated into a planetoid that exploded and got strewn about. But that iron could have come from the core of a massive star, like a 40 solar mass star, but also might have been made in a supernova, because there's no reason why you can't also make iron in a supernova explosion.
Right. Okay.
So it could be either.
Okay.
So I hope that answers the question. I'm not sure. There's the iron here, by the way. There's the iron.
Thank you. We have 2 more main questions, but we're running out of time because I do have to run right at 5 o'clock. Real quickly, Walter asked, is the frequency of newborn stars and dying stars known, for example, in the Milky Way? And I believe you had percentages like abundance of each of the types of stars on one of your slides. So Walter, if you want to, check that out.
Yeah, you can wind back and look. Yeah.
This video is on our YouTube channel, so you can go and watch it back and take a look at that. And then one last question, which we absolutely do not have the time to cover today, and we might have to do a whole separate topic on it, which is from Cicely. Tell us more about pulsars. What are they? What do they tell us? What might we be missing? We may have to do a whole separate episode on things like pulsars.
We'll do an episode on radio astronomy, and we'll cover them then.
Yeah, because then there's also magnetars. I don't know. There's just so much cool stuff. So I have noted down some suggestions for future sessions. Chris and I will keep talking about it. Thanks everyone for joining. It was lovely to see you all again. Victoria's super excited about a radio astronomy episode. We need to maybe recruit some experts on that too. We'll see you all in 2 weeks. Our next episode is on October 12th, and we're talking about astronomy at other wavelengths, right? That's the next one?
Yeah.
Yeah, so we're also going to be talking at that one about the James Webb Space Telescope, and I'm so excited because the James Webb Space Telescope has a launch date, and it is December 18th this year, and I'm so excited because it's been a long time coming. So we're going to talk about a whole bunch of different telescopes, but the James Webb Space Telescope as well. I think that's it. Thank you so much, Chris. Do you have anything else you wanted to add?
Just take advantage of the cool, clear evenings, and let us know if you see any of these objects. Let us know if you image the Spaghetti Nebula or the Helix, some of those cool ones. Hopefully you 100%. Give those a try. Yeah.
And yeah, this is a really great time to go observing. So the nights are early. It's not too cold. It's not winter cold. And I will, I hope that you have a great time in the next 2 weeks. We'll see you in 2 weeks. Chris, thank you so much for all of your help with this show in general, but especially with this episode because you did so much. We'll see you all soon.